Group Theory and its Application to Music. So for the members, we have Jade Palma, Hermudo Elmer Cadavid, Truly Yours, Jerjan Emea, and Abuda Chris Ladi. So group. In math, group is a collection of elements that might be a face of a Rubik cube, patterns, and musical notes. So music. It is a big field within mathematics, and lots of different people have taken it in different directions. So music is one of the fine arts, which concern is with the combination of sounds with a view to beauty and form and expression or feeling. So music itself is not complete without musical notes. So and that musical notes are C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and B. So in mathematics and abstract algebra, group theory studies the algebraic structures known as group. So the concept of a group is central to abstract algebra, such that this must satisfy the required specific rules or axiom. So we have the closure, the associativity, identity, inverse, and lastly the commutative or abelian.
Good everyone, my name is Almar Hermodo, and now I'm going to continue the report, which is the group theory and its application to music. So let G be a set together with a binary operation usually called multiplication that assigns to each ordered pair AB of elements of G an element in G denoted by A times B. We say G is a group under this operation if the following properties are satisfied. So these properties are the closure, associativity, identity, and the inverse. So first is closure property. Closure property can be defined as the closure of a set of numbers by using arithmetic operations and is completed by those operations. In other words, when the operation performed on any two numbers from the set and the result obtained will be the number from the set itself is considered to be closed. That is the closure property. And the second one is associativity. Associativity is the operation is associative, that is AB times C equals A times BC for all A, B, C, and G. So that is associativity. And the second one is identity. Identity is there's an element A called the identity in G such that A times the identity equals the identity times A equals A for all A and G. And the inverse is for each element A and G, there is an element B in G called an inverse of A, such that AB equals BA times the identity. So that is the inverse. So I'm going to give an example, but this example will not related in musical, but music. But later one of my groupmate will give an example related in music. So first is closure. So closure, if we multiply the numbers in a given set, and the result will be in the set itself. So let's have 2 times 4 is 8. So the result is in the set itself. So the closure property is checked. And the next one is associativity. So associativity is AB times C equals A times BC. So under the operation addition, so A plus B plus C equals A plus B plus C. So let's have 2 plus 4 plus 6, and also 2 plus 4 plus 6 will also give the same answer. So associativity is check, and the identity is let's have A is 2 and the identity is 0. So A plus 0 is equal to 0, and also in the opposite one, identity times A, so 0 plus 2 is equal to 2. So the identity is checked. So that's the part of my report. The next one will be Mr. Abuda. He will continue my report. That's all.
Hello everyone, my name is Chris Abuda, and I'm going to discuss the continuation of the properties, which is the inverse. In inverse, for each element A in G, there is an element B in G called an inverse of A, such that AB is equal to BE is equal to the element. So using A asterisk, the inverse of A is equal to the element. So we put 2 because our problem is, example problem is the all positive even integers. So we use 2 for A plus the inverse of 2, which is 2 raised to negative 1. So 2 plus negative 2 is equal to 0, which is our element is 0. So inverse is satisfied for our example. Next is the commutative or the abelian. So in abelian, if a group has the property that AB is equal to BA for every pair of elements A and B, then say that group is abelian or commutative. So in our example, which is all positive even integers, is abelian or not. Using the abelian, AB is equal to BA. So we put 2, which is our A, and 4, which is our B. So 2 plus 4 is equal to BA, which is 4 plus 2, so equals 6. So in our example, which is the all positive even integers, is a abelian group. And that's all of my part. Thank you.
Thank you, Chris and Elmer, for your discussion. Okay, let's proceed to what is music. So, music is generally defined as an art of arranging sound to create some combination of forms, harmony, melody, rhythm, or otherwise expressive content. So, now what is octave? Octave or a perfect octave is an interval between one musical pitch and another with double its frequency. The octave relationship is a natural phenomenon that has been referred to as a basic miracle of music, the use of which is common in the most musical system. And now we have here the octave intervals. So first, we have here a 5 octave intervals. First is the P, which is the perfect unison. Second is the M, which is the major. Third, this is the minor. So this is the minor. And the fourth is the augmented. And the fifth is the diminished. Sorry. So next, we have here the 12 basic piano chords with of the beginning. So instead of using other chords, I prefer to use the chords of the piano, which is we have here 12 chords. We have first the C sharp, D, the D sharp, E, F sharp, G sharp, A sharp, and B. Next, so our first example. So we have here the problem modulo 12, which is have an elements of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And each elements of the modulo 12 has a corresponding octave scales. So the corresponding of 0 is P1, which is the perfect 1. The corresponding of 1 is a minor 2. The corresponding of 2 is the major 2. The corresponding of 3 is the minor 3. The corresponding of 4 is the major 3. The corresponding of 5 is the perfect 4. The corresponding of 6 is diminished 5. The corresponding of 7 is perfect 5. The corresponding of 8 is minor 6. The corresponding of 9 is major 6. The corresponding of 10 is minor 7, and the corresponding of 11 is equal to major 7. So each octave intervals have also a correspond chords in the chords. The corresponding of perfect 1 is C. The corresponding of minor 2 is C sharp. The corresponding of major second is D. The corresponding of minor third is D sharp. The corresponding of major third is E. The corresponding of perfect 4 is F. The corresponding of diminished 5 is equal to F sharp. The corresponding of P5 is equal to G. The corresponding of minor 6 is equal to G sharp. The corresponding of major 6 is equal to A, the corresponds of minor 7 is equal to A sharp, and the corresponds of major 7 is D. And now, we should apply first, we should apply the 5 actions, which first is the closure. If we should find if it is satisfied or not. So, first is the closure. Okay, I use A plus B is equal to R. So, we already know that the closure, if we add both two elements, still the result is in the elements, still in the given element. So we assume that our dominant here is 7, which is corresponds by the perfect 5, and the chords is G. So the chords is G. So this is our dominant 7. Now the corresponds of P5 is 7. So our 7 here. So we already know that we assume that our identity is 0. So it is obvious. It is obvious because if we in addition property, we should use the positive, which is the addition. So we should use the 0. We can prove that our identity is 0 because if we add any number can be added in 0. Still the answer is in the elements. So that's why our identity here is 0. So 7 is equal to 0. So the 0. So 0 is corresponds by the perfect 1, which is the corresponds of the chord C. And now 7 plus 7 is equal to 14. So 14. So in 14 we have in modulo 12 we have two it is equivalent by 2. So if we find the corresponding octave scales of 2, which is major 2, and in the chords of the piano it will be equivalent of D. So in the addition mode 12, the equivalent of this is 2. So can you next? So it's satisfied, it's whole because it's any number. If we add both A and B, still the result is in the elements. Okay. Stop. Okay. Did you notice that we have here three chords? How we get the chords here? So here we have a D, we have a G, and we have a D. So how we define these chords? So first in the closure we have a 7, which is our dominant. So 7 is the equivalent of P perfect 5, which is the chords of G. So the G here is here. So that's why we have a chords G. And now why we get the D? So we get D because 7 is equal to 0 based on our identity is 0, which is 7 is equal to 0. So the correspondence of 0 is equal to C. C. That's why we start here, C. And now we have D. Why did we get how we get the D? Because for 7 plus 7 is equal to 14, and 14 is equal to the modulo in the modulo 12, it is equal to 2. Then the equivalence of 2 in the octave intervals in the chords is D. So that's why we have here 3 chords. Can you play? Okay, continue. And now, let's proceed to the second properties or actions. So the second is associativity. So same here, we have here a problem, which is the modulo 12, stating the elements, the octave intervals, and the chords. So we have a formula here. So AB times C is equal to A times BC for all A and B, C. So it means if we use the binary operation, that result should be the same and balanced. So we assume that we have equation here, which is the minor second plus perfect 4 plus perfect 4. Yeah, we use addition because we have in modulo 12, so it's expected our binary operation is addition. So plus minor 6 is equal to major 2 plus perfect 4 plus minor 6. So if we will substitute it by the corresponds value in the elements, so the corresponds value of the major 2 is 2, the corresponds value of 4 is 5, the corresponds value of minor 6 is 8, and the same here. and now we will substitute, and 7 plus 5 is equal to 2 plus 5 is equal to 7 plus 8 is equal to 15. So 15 in the right side. 5 plus 8 is equal to 13 plus 2 is equal to 15. So it balanced. So it means it's satisfied. Why did we get how did we get these chords? Because in the modulo 12, the value of the 15 is 3. Because 3, where is the 3? You see, here is the 3. So the equivalent octave scales is the minor 3, and the chords is the D sharp. Okay, now let's proceed to it. It's satisfied. So next, let's proceed to the identity. So this is the third identity. So this is the formula of the identity. So A is equal to A is equal to A. So it means we should use our binary operation. This is the addition. Then the result should be A. So we assume we should assume that R is 0. So if we add 0 plus 0 is equal to still 0. If we also if we assume that RA is 1, so A plus 1, 0 plus 1 plus 0 or 0 plus 1 is still equal to A. So any elements, any value of A that will if we use the binary operation, the result still in the elements and still is A. So it means here in the given problem, so our problem is satisfied in the third properties, which is the identity. And the fourth properties is the inverse. So the formula of inverse is A binary operation, and the inverse of A is equal to inverse of A binary operation A is equal to E. So here the result should be the identity. So which means that our identity here is 0 because we are in modulo 12. So for instance, our P5 in the interval, it is equivalent to 7. So did you remember that the equivalent of the P5 is equal to 7, which corresponds to G in the chords. And if we use this A, which 7 is inverse, is negative 7, so the result will be the identity. So because if we in the elements of the modulo 12, any numbers can be used. Still the result is still 0 because if we add the inverse to still itself, the result should be 0, and now it's satisfied on the whole to our problem. Okay, next. So the fifth is the permutative or abelian. So we know that abelian is if we add or multiply A and B, AB and BA, the result should be in the elements. So assume that our major minor 2 and plus major 2 is equal to major 2 plus minor 2. So in the previous problem, we use the equivalent elements of the minor 2 is 1, and the equivalent of my major 2 is 2. Now, if we add 1 plus 2 is equal to 3, and 2 plus 1 is equal to 2, so it balances. So still, the answer is still in the element, so it's a abelian or it's a commutative property. So the chord, how we get the chord, because in the chords, the value of the correspondence of 3 is the chords of major the correspondence of 3 is D sharp. So still D sharp is the value in the music scale. So it's satisfied. So that will be my part. So thank you and God bless.